Today, we're pulling back the curtain on a secret weapon. It's a tool that data scientists use to sorta, see the future. Or, at the very least, make some amazingly good guesses about it. We are diving headfirst into the world of probability distributions.
Okay, so this sounds like the beginning of a really weird joke, right? A doctor, a web dev, and a car designer walk into a bar. But what if I told you they all rely on the exact same powerful concept to do their jobs? Well, that's exactly what we're going to unpack.
You know, the world around us is just messy. It's full of randomness. How many people are going to show up to the party? Will the stock I bought go up or down? Is it actually going to rain next Tuesday? This uncertainty, this variability, that's the big challenge when you're trying to make sense of any kind of data. And this is it. This is our secret weapon. A probability distribution is basically a roadmap that tells us the chances of all the different possible outcomes. It's how we can take all that chaotic, random data and find the hidden patterns inside. It's how we start to make sense of the mess.
So, to really see how this all works, we've got to start with one very simple, very fundamental idea. It's the building block for everything else.
And that building block is called a random variable. Now, I know that sounds a little intimidating, but it's actually super simple. It's just a way of sticking a number onto a random event. See, you can't really do math with words like heads or tails, but you can absolutely do math with numbers like 0 and 1. So a random variable just translates the real world into the language of math.
Okay, check this out. It's a perfect example. Let's say we flip a coin 3 times. We can create a random variable, we'll call it x, and just say it's the total number of heads we get. So if we get heads, 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 our x is 3. If we get tails, 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 our x is 0. And boom, just like that, we turned a bunch of coin flips into a clean set of numbers we can actually work with.
All right, so now that we have these random variables, you need to know that they come in 2 main flavors. And trust me, knowing the difference is absolutely crucial. So on one hand, you've got discrete variables. Think of these as things you can count. You know, like the number of kids in a family. It can be 0, 1, 2, or 3, but it can never be 2.5. On the other hand, you've got continuous variables. These are things you measure, like rainfall. It can be 2.5 inches, or 2.51, or 2.513 inches. It can be any value in a range. This difference between counting and measuring, it changes everything.
So, let's start in the world of counting. When we're dealing with those discrete, countable numbers, we need a special set of tools called discrete probability distributions.
One of the most common ones you'll ever see is the binomial distribution. This is your go-to tool for any situation that has only 2 possible outcomes. We're talking yes or no, pass or fail, win or lose. For simplicity, we just call them success and failure.
So, how do you know if you've got a binomial situation on your hands? Well, there's a handy 4-point checklist. First, you need a fixed number of tries, like flipping a coin 10 times. Second, each of those tries has to have only 2 outcomes. Third, the chance of success can't change from one try to the next. And finally, you have to be counting the number of successes. If you can check all 4 of those boxes, you're in business. Let's make this real. Imagine a researcher studying a new shoulder surgery on 20 patients. Okay, that's our fixed number of trials. We know from past data the surgery has a 92% success rate, and that probability is constant. They want to know the odds that exactly 18 of those 20 surgeries are successful. See, this fits that checklist perfectly. The binomial distribution can give them a precise answer. All right, on to our next tool for counting, the Poisson distribution. Now this one's a little different. It's not about a fixed number of tries. Instead, it's all about counting how many times something happens over a certain interval, like a period of time or a specific area.
And hey, this is where our website developer from the intro comes back into the picture. They could use a Poisson distribution to predict how many users hit their site in any given minute. Or a city could use it to figure out the probability of car accidents at an intersection each month. The key here is always the same. It's the number of events per interval.
Okay, so we've talked all about counting. Now let's switch gears and jump into the world of measurement, the world of continuous data.
And in this world, there is an absolute rock star. It's the normal distribution. But you probably know it by its much more famous nickname, the bell curve. All because of that iconic, symmetrical shape it has.
Now, the real magic of the bell curve comes from something called the empirical rule. Basically, it works like this. You figure out the average value, or the mean. Then you calculate something called a standard deviation, which is just a fancy term for a typical step size away from that average. The rule says that about 68% of all your data is going to fall within one of those steps of the average. If you take 2 steps out, you've just captured about 95% of everything.
Let's really focus on that 95% number for a second, because it is the golden number in so many industries. It represents pretty much everyone, leaving out just the super rare extreme cases on either end. For engineers and designers, hitting that 95% mark is often the perfect sweet spot. It means you're building something that works for almost everybody, without going crazy trying to account for every single outlier.
And that brings us right back to our car designer. Human height tends to follow a normal distribution, a bell curve. So the designer can use that 95% rule to figure out how far the car seat needs to slide forward and back. By designing it for that 95% range, they make sure almost every single driver can get a comfortable fit. And there it is, the secret weapon in action.
So, we've looked at the world of counting and the world of measuring. Let's wrap this all up by seeing how these ideas become the real engine of modern data science.
You know, the binomial, the Poisson, the normal curve, these aren't just cool theories from a textbook. They're the actual foundation that data scientists build everything on. They're what power predictive models and what let us test our ideas about the world in a way that's backed up by math.
And look, this isn't just an academic thing. As the experts at Goovy point out, these concepts are redefining how organizations approach problem solving and strategy formulation. We're talking about a fundamental shift from making decisions based on a gut feeling to making them based on actual data.
So what's the bottom line here? Probability distributions are our best weapon for taming the randomness of the world. We use discrete distributions, like binomial and Poisson, when we're counting stuff. And we use continuous ones, like the normal curve, when we're measuring stuff. And when we use them right, they let us turn raw, messy data into incredibly powerful and useful predictions.
Once you understand these patterns, you start to see the hidden order in all the chaos around you. So the only real question left is, now that you know about the secret weapon, what are you going to predict?
Have you ever found yourself trying to put a number on maybe? Like, how likely is it really going to rain tomorrow?
Yeah, or what are the actual odds your team wins the championship?
Exactly. Or even bigger stuff, like what's the probability this new business idea will actually work out? We're always trying to quantify the unknown.
Trying to tame that uncertainty.
Right. So today we're doing a deep dive into the language we use for that, probability.
That's the plan. Our mission really is to unpack the fundamental ideas of probability. It's way more than just math theory. It gives us this incredibly powerful framework for making sense of randomness and for making, frankly, smarter decisions in all sorts of fields.
Medicine, finance.
You name it. We've pulled together insights from, academic texts, financial analyses, real-world examples, even some pretty interesting online discussions to give you a really comprehensive view.
Okay, so let's start right at the beginning. We all kind of get chance, but what is probability, fundamentally, when you try to pin it down?
Well, at its heart, probability is simply the numerical description of how likely an event is to occur.
Just a number.
Just a number, always between 0 and 1. Or, 0% and 100% if that feels more intuitive.
Okay.
Like the classic example, a fair coin flip. The probability of getting heads, P's, it's just 0.5. Simple as that. It forces us to be precise.
Right.
Move beyond just maybe to how much maybe.
But, okay, that 0.5, lots of people think if they flip a coin twice, they have to get one head, one tail.
Yeah.
What's the big misunderstanding?
Yeah, that's a huge one. Yeah, it's the gambler's fallacy, this idea that past flips somehow influence the next one.
Right, I've had 5 heads, the next must be tails.
Exactly, but the coin doesn't remember. Each flip is independent. Now, over thousands of flips, it'll get close to 0.5, but in the short term, anything can happen. That 0.5 is just the chance for each single flip.
Gotcha.
And to talk about this properly, we use some key terms. An outcome is just any possible result, heads, tails, rolling a 3. An event is a specific outcome, or maybe a group of them. Like the event of rolling an even number is getting a 2, 4, or 6.
Right, makes sense.
And then there's a random variable. This one sounds a bit abstract, maybe.
Yeah, a little bit. What's its job?
It's basically our translator. It takes something we observe, like heads or jack of spades, and gives it a number, a numerical value.
Ah, so we can do math with it.
Precisely. That's the key.
Yeah.
It lets us move from just watching stuff happen to actually calculating and predicting things. You turn the thing into a number.
Like the card example from one source. You assign numbers 1 to 13 to cards. Jack itself can't be the random variable value. It has to be, say, 11.
Exactly. Math needs numbers. Sorry, Jax.
So we've got the core idea, the terms. But how do we actually figure out a probability? Are there different ways?
Yeah, broadly speaking, there are three main ways. First, theoretical probability. That's based purely on reasoning. Like, we know a fair coin should be 50-50 before we even flip it. Then there's experimental probability. That comes from actually doing the experiment. Flip the coin 100 times, get 53 heads. Your experimental probability is 0.53.
Based on what happened.
Right. And finally, subjective probability. This one's based on personal judgment, experience, maybe intuition. You see this a lot in finance for unique events that won't be repeated exactly.
So different tools for different situations. Okay, this next bit seems really important. As we try to measure randomness, not all unknowns are the same, are they? It matters if we're counting things or measuring things.
Absolutely fundamental difference. This brings us to discrete versus continuous random variables.
So discrete is countable.
Exactly. A discrete random variable has a finite or countable number of values. Think things you count. Number of cars in a lot. Number of kids in a family.
Can't have half a car.
Precisely. It jumps from one whole value to the next. 15 cars, 16 cars. Not 15.37.
Okay, so discrete is counting. Continuous.
That's right. A continuous random variable can take on any value within a certain range. Think weight, height, time, temperature.
Like the bag of apples example. It could weigh 2.45 pounds, or 2.457, or 2.45734.
Exactly. It's smooth. It doesn't have those jumps. Any value is theoretically possible within the range.
And why does this distinction matter so much?
Because the statistical tools we use are completely different. If you're analyzing discrete data, counts, you use one set of methods. If you've got continuous data measurements, you need a whole different toolkit.
Like the examples. Number of children per household. That's clearly discrete. You count them.
Right.
But the amount of rain in inches. Continuous. It
Yeah.
could be 2 inches, 2.1, 2.05, 2.056.
Yep. Getting this right, discrete or continuous, is step one before you can really do any meaningful analysis. It dictates the path you take.
Okay, so let's dive into the discrete side first. When we're counting things, we have some really specific, powerful tools, right? These distributions.
We do. Two of the workhorses are the binomial and the Poisson distributions. Let's start with binomial.
Binomial. Sounds like 2.
Exactly. It's used when each trial, each observation, have only two possible outcomes. We usually call them success and failure.
Okay, like heads or tails.
Yeah.
Or maybe pass or fail on a test.
Perfect examples. Or maybe a patient's surgery is successful or not. The key things are, you need a fixed number of trials. The trials have to be independent of each other, and the probability of success has to be the same for every single trial.
Right. And you mentioned success doesn't always mean good.
Crucial point, yeah.
Yeah.
If you're studying smoking rates, finding someone who smokes might be coded as a success for your data collection purpose, even though smoking itself isn't good. It's just the outcome you're counting.
Got it. It's just the label for what you're looking for. So that example about shoulder surgery. A researcher studies 20 patients, knows the success rate is, say, 92%. The binomial distribution lets them ask, what's the probability that exactly 18 out of the 20 are successful?
Precisely that kind of specific counting question. And yeah, the formula involves factorials. It can look messy.
But we use computers now.
Thankfully, yes. Tools like Python's scipy.stats, you just plug in the numbers binom.pmf, and it gives you the answer. Saves a lot of headache.
Okay, so that's binomial for fixed trials with 2 outcomes. What about the other one? Poisson.
Right, the Poisson distribution. This one's different. It's about counting the number of times an event happens within a specific interval.
Interval. Like time or space.
Exactly. Could be time, area, distance, volume. The key is you're counting occurrences over some continuous interval, and the events happen independently.
Okay, give me some examples.
Think about a website owner. They might want to know the probability of getting, say, 10 users in the next minute. Or a city planner might look at the number of accidents at a specific intersection per month.
Ah, so it's about rates. Occurrences per unit of something.
That's a great way to put it. Rates. The source example was a traffic engineer. If they know the mean number of cars entering a garage is 7 every 10 minutes.
They can use Poisson to figure out the probability of, say, exactly 9 cars entering in the next 10 minutes?
You got it. Again, based on that known average rate. And just like binomial, software handles the calculations easily.
All right, so we've covered discrete counting. Now let's shift gears to continuous measurements. And there's one shape that just dominates here, right? The bell curve. You see it everywhere.
You really do. The normal distribution, that classic symmetrical bell shape, is incredibly common.
Why, though? Why that shape?
It often arises when a variable is influenced by many small, independent, random factors. Think about human height. It's affected by genetics, nutrition, lots of little things acting together. That tends to result in most people clustering around an average height, with fewer people being extremely tall or extremely short.
So lots of things kind of average out in the middle.
In a sense, yeah. And it applies to so many things: weights, salaries, blood pressure, test scores. It's defined by just two numbers. The mean, usually written as I/O, which is the center peak of the bell,
The average.
right? And the standard deviation, sigma, which tells you how spread out the bell is. Is it tall and skinny or short and wide?
Okay, mean and standard deviation. Got it. And you mentioned standardizing using z-scores. What's that about?
Z-scores are super useful. Basically, they translate any value from any normal distribution into a standard scale. A z-score tells you exactly how many standard deviations a particular data point is away from its mean.
So you can compare different things. Like, is someone's salary relatively higher than someone else's height compared to their respective averages?
Precisely. It puts everything onto the same playing field, the standard normal distribution, which always has a mean of 0 and a standard deviation of 1. This makes comparing things and calculating probabilities much easier.
Again, we don't need to do complex calculus by hand, right? Software helps.
Definitely. Functions like norm.cdf in Python libraries
Yeah.
calculate the cumulative probability, basically, the area under the curve up to a certain point.
Like the example, calculating the chance an employee earns more than $68,000, given the average is $60K, and the standard deviation is $7 5Ks. The software finds that area under the curve for us.
Exactly. It translates that z-score into a probability.
Now, there's also a quick rule of thumb, isn't there? The empirical rule.
Yeah, the empirical rule of the 68, 95, 99.7 rule. It's a great shortcut for normally distributed data. So roughly 68% of your data falls within one standard deviation of the mean.
Okay.
About 95% falls within 2 standard deviations.
So most of it.
Right. And almost all of it, 99.7%, falls within 3 standard deviations.
How is that useful in practice?
Well, take the car seat example. An automotive designer wants to design seats comfortable for, say, 95% of people. They'll look at average heights, maybe the mean is 68 inches, standard deviation 3 inches.
Okay.
2 standard deviations is 2 times 3, so 6 inches. They design the seats to fit people roughly between 68 minus 6, which is 62 inches, and 68 plus 6, which is 74 inches. That range covers the middle 95%.
Wow. So that rule directly impacts product design. Makes total sense. Okay. So far, mostly events happening on their own. Coin flips, individual salaries. But the real world is messy, right? Things are connected. What happens when one event changes the odds of another?
That's where conditional probability comes into play. It's all about how probabilities change when you get new information.
Conditional. So based on a condition.
Exactly. It measures the probability of event A happening, given that event B has already happened.
Yeah.
We write it as PAB, probability of A given B.
Okay, PAB. How's that different from just like the probability of A or A and B both happening?
Good distinction.
Uh-huh.
The simple probability of A is called marginal probability. The probability of A and B both happening is joint probability.
Right.
Conditional probability, PAB, uses the joint probability. The formula is PAB equals PA and B divided by PB.
Yeah.
It asks, out of all the times B happens, how often does A also happen?
Okay, so it's like zooming in. If I know B happened, what are the chances for A now?
Perfect way to think about it.
Yeah.
You've updated your knowledge. Think about that marble example from Investopedia. Bag has 6 red, 3 blue, 1 green marble, total 10.
Okay.
What's the probability of drawing red? P red. It's 6 out of 10.
Right, 610.
Now, what's the probability of drawing red given the marble drawn is not green? P red, not green.
Ah, okay. So if it's not green, there are only 6 red plus 3 blue equals 9 possible marbles left.
Exactly. Your world just shrank from 10 possibilities down to 9.
And out of those 9, 6 are red. So 69 or 23.
You got it. The condition not green changed the probability from 610 to 69.
That makes sense. It's like filtering the possibilities. The dice example too. Probability of rolling an even number given it's greater than 4.
Right. Greater than 4 means only 5 or 6 are possible.
2 possibilities.
And of those 2, only 1 is even, the 6. So 1 out of 2, the probability is 12.
The condition greater than 4 totally changed the odds from the original 36 or 12 for rolling any even number. All right, so we know how to calculate probabilities, even conditional ones. But what should we actually expect to happen on average, and how much might things vary around that average?
Now you're talking about expected value and variance, 2 super important concepts.
Expected value sounds like what you'd expect.
Pretty much. It's often written EX or mu. It's the long-run average outcome if you could repeat an experiment many, many times. Think of it as the theoretical average.
Like the die roll example. You can't roll a 3.5.
Right, you roll a 1, 2, 3, 4, 5, or 6. But if you rolled it thousands of times and averaged all the results, that average would get really close to 3.5. That's the expected value.
Even though it's not a possible outcome on any single roll?
Exactly. It tells you the center of gravity, the long-term balancing point of the probabilities.
Okay, so that's the average expectation. What about variance?
Variance, written sigma sigma squared, or sometimes sigma, measures the spread or dispersion of the possible outcomes around that expected value, the mean.
So how much things jump around?
Yeah. High variance means the outcomes are spread way out. Lots of variability, maybe high risk. Low variance means the outcomes are tightly clustered around the mean, more consistent, predictable.
So expected value tells you the target. Variance tells you how bumpy the ride might be.
That's a great analogy. Expected value is the destination on average. Variance is the turbulence.
How are these used?
Oh, everywhere. Finance uses them constantly to assess investment risk versus potential return. Insurance uses expected value to set premiums. In manufacturing, variance helps monitor quality control. You want low variance for consistent products.
And in machine learning.
Big time. Evaluating model performance often involves looking at bias related to expected value, like is the model accurate on average, and variance. How much do the model's predictions change with different training data? It's fundamental.
Okay, this next part sounds interesting. Apparently, there's a bit of a philosophical debate in statistics about how to even interpret probability. Frequentist versus Bayesian.
Yeah, it's a fascinating split, and it really affects how people approach data analysis. Two major schools of thought.
So what's the core difference? Let's start with frequentist. Sounds like frequency.
That's the key. The frequentist approach sees probability as the long-run frequency of an event if you could repeat the experiment, well, infinitely many times.
Like the coin flip again. It's 0.5 because over many flips, half will be heads.
Exactly. For a frequentist, parameters like the true probability of heads are fixed, unknown numbers that we try to estimate. Their methods, things like p-values, confidence intervals, are designed to make statements about how often certain results would occur in repeated experiments.
Okay, focused on long-run repetition. What about the Bayesian approach?
The Bayesian approach is different. It treats probability as a degree of belief about something happening, even if it's a one-off event you can't repeat.
A degree of belief. So more subjective.
It incorporates prior beliefs, yes. Bayesians start with a prior distribution, what you believe about a parameter before seeing the data. Then they use the observed data to update that belief, resulting in a posterior distribution.
So a belief plus data equals updated belief.
Kind of, yeah. Parameters themselves are treated as random variables that have distributions. It's about updating your state of knowledge.
That Android phone example really highlighted this, didn't it?
It did. A frequentist might say, the probability someone is typing on Android right now is either 0 or 1, they are or they aren't.
Right.
It's hard to assign a probability between 0 and 1 to a single fixed event.
Right.
But a Bayesian could easily say, based on market share data and maybe some other info, my degree of belief that this person is using Android is, say, 0.64. They can assign a probability reflecting uncertainty about a single instance.
So different tools for different kinds of questions, almost.
Definitely. And both systems are logically consistent internally. Frequentists often emphasize objectivity, while Bayesians acknowledge subjectivity in the prior. But, even frequentists make subjective choices about which models to use or what hypotheses to test.
So the line isn't always perfectly sharp.
Not always. It's a really deep topic, but understanding the core difference long-run frequency versus degree of belief is key.
Okay, let's talk about why bigger samples are generally better. Why do we trust those huge surveys more? There's a formal idea behind this, right?
Absolutely. It's the law of large numbers, often called the LLN. It's actually quite intuitive.
What does it say, formally?
It says that as you increase your sample size, as you collect more and more observations, the average result you see in your sample will get closer and closer to the true average of the entire population you're sampling from.
So the more data, the closer your sample average gets to the real thing.
Precisely. Think about insurance companies. With data from millions of drivers, their estimate of the average claim cost becomes incredibly accurate. Or election polls. A poll of 10,000 people is generally much more reliable than a poll of 100.
Because the sample average has had more chance to get close to the true population preference?
Exactly. Now, the LLN is about the average converging. There's a related but distinct theorem called the central limit theorem. or CLT.
Okay, how's the CLT different?
The CLT is amazing. It says that if you take many large samples from any population, even a really weirdly shaped one, and you calculate the average for each of those samples, the distribution of those sample averages will itself look like a normal distribution, a bell curve.
Whoa. So even if the original data isn't bell-shaped, the distribution of the averages of samples from it will be. If the samples are big enough.
That's the magic of the CLT. It's incredibly powerful because it lets us use all the tools we developed for the normal distribution to analyze sample averages, even when we don't know what the original population looks like.
That's huge for statistical inference.
Absolutely foundational.
Now, sometimes you hear law of large numbers used, like in business, about big companies struggling to maintain huge growth rates.
Yeah, that's a more colloquial use, like it's harder for Tesla to double its size now than it was when it was tiny.
Right.
It's not the statistical LLN, but it captures a similar idea. Scale changes things. As numbers get very large, percentage changes often become smaller. It's related to the idea of averages and limits, just in a business context.
So we've covered a ton of theory, but it's worth remembering that actually doing this stuff is much easier now, right, with technology?
Oh, absolutely. For data scientists, tools like Python's scipy.stats library are indispensable. Calculating a binomial probability.binom.pmf. Need a probability from a normal distribution, norm.cdf. The software handles the heavy lifting.
Takes the scary math out of it, lets you focus on the concept.
Exactly. And that accessibility means probability is used everywhere. We've touched on so many applications.
Medical diagnosis, financial forecasting.
Engineering reliability. How likely is this bridge to last 100 years? Quality control in factories, keeping products consistent. Understanding complex systems like climate models or ecosystems.
And machine learning, which we mentioned. It seems like probability underpins so much of how AI learns and predicts.
It absolutely does. Concepts like the bias variance trade-off and model building are pure probability and statistics. Bayesian methods are used extensively in certain types of machine learning. It's really the bedrock language for dealing with uncertainty, which is what data science is often about. #tagoutro.
Wow, okay. That was quite the deep dive. We went from the absolute basics, what is probability, through discrete versus continuous variables.
Looked at key distributions like binomial, Poisson, and that all-important normal distribution.
Untangled conditional probability, expected value, variance, even touched on the frequentist versus Bayesian philosophies.
Yeah, it's a lot, but hopefully it provides a clearer picture. Probability isn't just some abstract math concept.
No, it really feels like a fundamental toolkit.
It is. It's a language and a set of tools for bringing logic, structure, to a world that's full of randomness. It helps us make sense of uncertainty and ultimately make better, more informed decisions.
In pretty much every field imaginable.
So here's something to think about as we wrap up. If, as we discussed, even the frequentist approach, which aims for objectivity, involves subjective choices like picking a model.
Right.
And Bayesian methods openly start with subjective degrees of belief.
Yeah.
Does truly objective prediction even exist?
Good question.
Or is mastering probability really about making the most transparent, the most rigorously informed, and the most logically sound subjective assessment you possibly can when you're facing the unknown?